Hello, today we're looking at a classic Calculus 3 problem, which is optimization with the constraint. We want to find the highest and lowest points of the function, which is f of x, y is equal to x of y. But we are restricted only to the points that lie on the circle x squared plus y squared is equal to 25. To solve this efficiently, we are going to use the method of LaGrange multipliers. First, we must write down f of x is equal to x of y. Then our constraint function is g of x is equal to x squared plus y squared is equal to 25. The foundational idea behind Lagrange multipliers is that the maximum and minimum values occur where the gradient of our objective function is parallel to the gradient of our constraint function. We express this mathematically using the Greek letter lambda as our scaling factor. Here's what it looks like. It's basically an upside down y. Okay. First, let's calculate the partial derivatives for both functions so we can set up our system of equations. For f of x, y, the partial derivative with respect to x is y, and with respect to y is x. For our constraint g of xy, the partial with respect to x is 2x, and with respect to y is 2y. Matching these up accordingly to our gradient formula gives us our system of equations. Let's write that down. X. And here are our constraint gradients. 2x, g of y, 2y. Then our system here looks like this. Y is equal to lambda 2x, and then x is equal to lambda 2y. And we have our constraint, which is x squared plus y squared is equal to 25. Okay, now eliminating the lambda. Now we need to solve the system. A great strategy here is to isolate lambda in the first equation by dividing both sides by 2x. Then we can substitute that expression directly into our second equation. Watch how the algebra simplifies cleanly. Let's write that down. We have y is equal to y 2x. And then for our substitute into our second equation, we have x is equal to y over 2x times 2y, which is equal to x is equal to 2y squared over 2x, and then that is equal to x is equal to y squared over x, and then that equals x squared is equal to y squared, and then that leaves us with square root that, and then we get y is equal to the plus or minus of x. This tells us a crucial piece of information at our extreme levels. X squared must equal y squared. We can take this relationship and plug it right back into our third equation, which is our original circle constraint. By substituting x squared in place of y squared, we can solve for x, which in turn gives us our exact coordinate values. Let's write that down. X squared plus y squared is equal to 25, which equals 2x squared is equal to 25. Then we gotta take away the 2. X squared is equal to 25 over 2, and this equals square root of that. X is equal to plus or minus 5 over the square root of 2. And since y squared is equal to x squared, that would also mean that y is equal to plus or minus 5 over square root of 2. Because both x and y can be positive or negative, this gives us 4 distinct critical points on the circle to test. Let's plug them back into our original objective function. which is this, if you forgot, to x, y. Okay, when the signs match up, the product is positive 12.5. When the signs are opposites, the product is negative 12.5. Therefore, our max value is 12.5 and our minimum value is negative 12.5. That is a complete solution using LaGrange multipliers. Now let's write that down. So we have right here 5 over square root of 2, comma 5 over square root of 2. So we know that f is equal to 25 over 2, which is just equal to 12.5, which would be our max. And then for our second point, which is here, let's do this. And for our second point, we have negative 5 over square root of 2, comma, negative 5 over square root of 2 is our second point. And as we've seen in the first point, it's the same thing. So f is equal to 25 over 2, which is equal to 12.5, which is also a max. And then for our mins, we have 5 over square root of 2 over 5 over negative square root of 2. We have f is equal to negative 25 over 2, which is equal to negative 12.5, which is one of our mins. It's our critical points. And then we also have negative 5 over square root of 2, comma, negative 5 over square root of 2. And then our point right here is going to be negative 25 over 2, which is equal to negative 12.5, which is another min. And that right there is how you solve using the LaGrange. What is it called? And that's how you solve using LaGrange multipliers.